We will now further study the behavior of sine and cosine and use the things we've just established to get some results on where the functions vanish. If we have some value in r, then the following holds. A, the sine of x is 0 if and only if x is of the form k times pi, where k is in z. Okay, similarly, the cosine of x is 0 if and only if x is has some odd number over 2, so 2k plus 1 over 2 times pi, where again k in z. Okay, how to see this? Okay, let's start with A. So first of all, the simple thing, we have to show that it's 0 everywhere there. We know, first of all, that we have seen that sine of 0 is 0, and we've seen just that this then shows that the sine of pi is 0. This was the theorem we just had, so theorem 386b. So the sign, shift given by pi just changes the sign, which is irrelevant here. And if we now iterate this again and again and again, so we can then show that the sine of k pi is 0 for all k in z. Simply because we always shift by pi and by pi and by pi and by pi and so on. Okay, now the other direction. So if it's 0, then it's in there. We will show this by proving the contraposition. If it's not in there, then it's not 0. Namely, first of all, we've seen by theorem 382, we've seen that the sign is positive on the interval from 0 to 2, the open interval. And this particularly shows that the sign is positive for all x in the interval from 0 to pi over 2, since we've seen that this is smaller than 2. Even the closed interval, because this is strictly smaller than 2. Okay, now so much for that. And now we've also seen, this follows from theorems 382 and 377e, that was the symmetry property, that the cosine starts at 1, it goes down, crosses 0, and becomes smaller and smaller and smaller. So by the monotonicity and by its symmetry property, it follows that the cosine is positive for all x in minus pi over 2 to pi over 2. But then, if we now take part C of the previous theorem, so, not theorem, corollary, sorry. This was also corollary, not theorem. I'm sorry. Corollary 386c, this implies that if x is between pi over 2 and 2, then we get the sine of x is the same as the cosine of pi over 2 minus x. And if x is chosen like this, it means that this number here is between minus pi over 2 and pi over 2. And we've just established that this is positive, and for all x in this interval, for all x in this interval. So we've seen that the sine of x is bigger than 0 for all x between 0 and pi. Now, by the symmetry properties, so the open interval from 0 to pi, so by iteratively using then this pi shifts, so iterating corollary 386b that we already used above, this shows that sine x is not equal to 0 for all k between two multiples of pi, so k pi and k plus 1 times pi. Okay, for all k in z. So this means any other point other than points in this set, there it's non-vanishing, so it shows the claim. So this shows the claim. Okay, so this completes the proof of A, and now to show B, to show the zeros of the cosine, we can just use this equation and what we just did. Namely, B then just follows from A and this identity, so corollary 386.C. Okay, good news. Okay, this is now what we've established. And this I now want to take a small break to see what we now know about sine and cosine, namely to draw their graphs. And I will only draw basically one period, because I'm sure you've already seen this already somewhere in high school. So I go from, let's take one more. So here is pi, and let's take the intervals pi, the points pi over 2, 3 over 2 pi. This would be 4 over 2 pi, and this would be 5 over 2 pi. So what we've seen so far, let's start with the sine. So we've seen that the sine is 0 here. Oh, and then we need 1 and minus 1. And it's bounded from above and below by 1 and minus 1. This is what we've already established. We've seen that this is 1 here, 0 here, minus 1 here, 0 here, and then by this periodicity here we get 1 again. And then you can show some nice monotonicity properties. We know that here it stays positive, and one then of course shows that it looks like this. Here, and then it starts again like this. Okay, this would be the sine of x, and for the cosine we've seen that here we have 1, here we have 0, and here it's also monotonically decreasing. Here we get minus 1, here we get 0, here we get 1, and here we get 0 again by these periodicities, and then it becomes like this, so it's just everything shifted by pi over 2. And this kind of reflects this shifting property that we just had in corollary 386. Okay, so these are the graphs. Now, another nice property that we get now is that we can basically use this also to solve some complex equations, as we shall see later on. So, for x and r, e to the ix is equal to 1 if and only if x is of the form 2k pi, where k in z. So if x is of this form. So how to see this? So this basically makes sense in terms of the angles. So we've seen that the points on this circle e to the ix is kind of angles. And we've seen that if we make one full turn, we are again back at 1. And because of periodicity, we can get around again and again and again and again. And this basically just says we always arrive then past 1 again, but nothing in between. So we only pass it at these points. So, but how to prove this formally? The sine of x over 2. This is by construction. 1 over, not by construction, but by a property that we derived before. This is 1 over 2i times e to the I times x over 2 minus e to the I times, e to the minus I times x over 2. Now, if we just pull out a factor of e to the minus I x over 2 over 2i, so this becomes e to the I x. This becomes 1. Okay, now we have this, and this is, this is some complex number which is definitely non-zero because the exponential function never becomes 0. So this equation here is 0, so which means that this is satisfied if and only if this is 0. So e to the ix equal to 1 if and only if the sine of x over 2 is 0. And we've seen that this sign vanishes precisely at these times k over pi. So x over 2 has to be of the form k pi, and this is that. So this implies already the statement by the previous corollary. So that was corollary 387. Yeah. Okay. Enough of the corollaries. Finally, I want to define the third trigonometric function that you probably all know. I won't work too much with that function. I will just define it and maybe later on use some properties, but this, so you've all seen it, namely the tangent function. So definition 389, the tangent function is the function tan minus pi over 2 to pi over 2 to r. Tan of x is defined to be the sine of x divided by the cosine of x. We've seen before that the cosine is positive on this interval, so that's indeed well defined. So this is a function. It's amazing. It's December, it's winter, and we still have a tan. Okay. So this is well defined, and let me just draw a graph. I won't motivate this in detail, but just so you know. So this goes from this interval to r, and it turns out that it really gets all of r, and it looks very roughly like this. So this goes to minus infinity, and this goes to plus infinity as we approach these values, which I won't prove, but which follows from the behavior, because there we see, of course, that these points here is where the cosine becomes 0, so we get problems here. So it goes to 0 in there, and this is how the tangent behaves. Okay. Now, now another theorem and definition combined, and this is also something I will not prove because that's not too important at the moment. It's also a construction that you just should see and that we will probably need later on. First of all, the cosine on the whole interval 0 to pi, so on this whole arc going from here down to minus 1, there it turns out that it's everywhere strictly monotonically decreasing, which we so far have shown only for this interval 0 to 2. Strictly monotonically decreasing. And it maps this interval 0 to pi bijectively onto minus 1, 1. Okay, and then we, of course, know from this continuity theorem that's from section 3.2 that, of course, now we have, this is bijective, we get an inverse. It's inverse arc cos, which now, so this is defined as the inverse function of the restriction of the cosine to 0 pi, which now looks really technical. So this as an inverse, which of course takes the other direction. We go from minus 1, 1 to 0 pi. This is called the arc cosine. Is continuous. This is then by this continuity theorem we had before. Okay, the same thing we can do for the sine, but we just need some different intervals. Namely, the sine, if we restrict this to minus pi over 2 to pi over 2, so it would be this arc here. I haven't drawn this fully, so if we would continue here to the left of this axis, we would again achieve the minus 1 here. So it would be a full arc going from minus 1 to 1 up. And as I've already indicated by drawing it, this is strictly monotonically increasing. And maps this interval minus pi over 2 to pi over 2 bijectively onto minus 1, 1, and its inverse, which is now written arcsine from minus 1, 1 to minus pi over 2 to pi over 2. Arcsine, this is now, arcsine, let me do it like this. This is defined as the restriction of sine to minus pi over 2 inverse. So this restriction here is continuous. This is again by the same result as before. Okay, part C is then the final result about this tangent, but we'll just, this is called the arcsine. Same way as the arc cosine. Okay, there's also an arctangent, as we shall see next. Oh, this probably can't see anymore. So let me just erase, and then we see the arctangent, and I won't do too much about these functions. As for the tangent, we have already restricted to a certain interval. Namely, the tangent is, I have defined it as a function from minus pi over 2 to pi over 2 to r. And this also has nice properties. This is first of all continuous. This is easy because it's a quotient of continuous functions, and we've seen that quotients are then again continuous. It's strictly monotonically increasing. Strictly monotonically increasing. And one can check that it's indeed bijective. As I've already indicated in the graph before, it's inverse. So this is called arctan, the arctangent. So this is simply 10 to the minus 1, which now goes from r to minus pi over 2 to pi over 2 is continuous. And this is called the arctangent. So the arctangent is continuous. Okay. Yeah, so much for that. So as I said, I won't prove this. This is a very technical, not that interesting. So this is contained in the lecture notes. Yeah, and basically we use this theorem about inverses of continuous functions on intervals. That was theorem 323. So we just use this for each of the three cases. Okay. Now let me quickly draw graphs of these three functions. So the first was the arc cosine. So this goes from 1 minus 1 to from 0 to pi, and it looks basically like this, like a bit like a rotated cosine. Okay, it's not symmetric. Sorry, I'll do this again. Okay, a bit like this. So this would be the arc cosine. Maybe click pause and go to Wolfram alpha if you want to see a proper graph of this. So for the arcsine, so here we have minus pi, then here would be pi, and I'm just asking myself why I made the axis so long anyway. From 1 minus 1, this now looks similar, but here we go from here to there, and there it takes a turn to this point. So this would be the arcsine. Oops. Arcsine of x, and the arctan looks quite interesting because we take all real values, and so the interesting numbers here are minus pi over 2 and pi over 2. And the arctan then goes here, if we go to infinity, to this, it approaches this line here, so this would be an interesting case of computing limits. And on the other side, it goes here to this part as we approach minus infinity. So the limit of going to infinity and so on. So here we could basically apply the things we did before, but I will not do this here just for time reasons. So this is the arctangent. Okay, one more thing I want to do with the exponential function, which is not directly related to this, but to the observations we had about how e to the ix describes angles and so on. This gives us a way of nicely describing complex numbers, which is sometimes much more convenient than the standard way of real and imaginary parts. Namely, these are the so-called polar coordinates. And this is not really good. It's December, it's freezing cold outside, so precisely the right time for polar coordinates. So, what does this say? This says, for all complex numbers, let's call them z, there are numbers r, which is a non-negative number, and a number phi in r, which is then to be an angle with, another Greek letter, okay, with such that we can write z as r times e to the I phi. And this is now kind of something that makes perfect sense from the intuition, as we shall see in a bit. First of all, if r is non-zero, then two of these representations coincide. So r1 times e to the I phi 1 is the same as r2 times e to the phi 2, if and only if r1 and r2 are equal, and phi 1 is phi 2 plus 2k pi for some k in z. Okay, before we prove this, let us kind of see how to interpret these numbers, and this is something which is probably more intuitive than just writing formulas. First of all, if we have z as r to the e phi, if we can write z like this, then the absolute value of z is r times the absolute value of e to the I phi, and this is always 1, so this is r. So this means r is the length of this number as a kind of a vector in R2. So if you draw the arrow in R2 connecting 0 to z, this is the length of it. So, yeah, let me maybe, this is the length of z. Let me put this in quotation marks. This will become more precise when we have vector spaces and so on, so much later. So phi, as we already observed before, this is the angle between z and the x-axis. And basically the positive x-axis, let's say 0 to plus infinity as a subset of C. And I'll draw you a picture in momentarily. First of all, phi is called the argument of z. Sometimes. So the argument of a complex number. Okay, now I draw the picture. So very simple. We've seen if this is C and we have a number Z. Okay, then we take the connection line here, the line segment to 0. Okay, then we have here, we have the angle phi, and then we have the length. So we only basically need to specify a direction and we need to specify a length, and this defines a point in C. So this here, the length of this is r. Okay, so anyway, it's just like we're sitting on a cannon or something. We have to rotate this into the right position and then take the wrong length to shoot at the right place. So that's the idea here. And of course, then you can see in this intuition, we've seen that this kind of rotates every time we reach 2 pi and 4 pi and 6 pi and so on. So basically, the symmetry is then reflected here. So if we just add a copy of 2 pi, this would just mean with our cannon we would rotate a few times around the circle before we go into this position, which doesn't matter in the end. Okay, so this is the angle here. And third point, and this is something that's also quite beautiful, namely if we have something in polar coordinates, the complex multiplication is a bit more intuitive than before. So assume we have some numbers r1 times e to the I phi 1 and r2 times e to the phi 2, e to the I phi 2. Then we get that z1 times z2 is r1, r2, e to the I, and now this rule of the exponential map of phi 1 plus phi 2. So this means if we view in the angle, this angle here is just the sum of the two angles of the two numbers before, and the length is the product of these lengths. So this would mean, yeah, maybe let me draw some quick picture here. I need some color chalk. So assume we have two numbers. We have z1, so yeah, this is C again. Assume we have some number z1. So this would be the angle phi 1, and here we would have the length r1. Now, assume we have phi, z2, which would be something like this. This would be z2, so this angle here is phi 2, and the length here is r2. So the product of these 2 points would then be the thing we get when we add the 2 angles. So this would be somewhere like maybe here. Oops, yeah, okay, now should have drawn nicer. Maybe I'll make this a bit shorter. Sorry about that. So let's say that these lengths multiply and assume that something is bigger than 1. So we maybe get something like this here, z1, z2. And this angle here is now the new angle. So this is phi 1 plus phi 2. And the length here is r1, r2. So this is what complex multiplication does, which is not that visible if you have just a pure definition in terms of real and imaginary part. Okay, so we still have to prove the theorem on polar coordinates. So proof of theorem 391. Okay, first of all, the easy part, the number z equal to 0. We can just write this as 0 times e to the I phi, and we can just choose some phi that we want. This becomes 0 anyway. So just some phi in R. So this case is obvious, so we can focus on z not equal to 0. In this case, we put R to be, yeah, we've seen before that here, if this R has this property, so this needs to be the absolute value. So this is what we can already define. We define R to be the absolute value of Z. And now we make a nice little trick. Namely, we say W should be Z divided by R. So this is just rescaling Z to the right position on the unit circle. And now we just need to take the right, we just need to reobtain the angle that this W has. So for this point, that A be the real part of W and B be the imaginary part of W. Okay, then A squared plus B squared is equal to 1 because we have this normalized and W is on the unit circle. So we can, first of all, this means that A and B are between -1 and 1, which means that we can define, first of all, the arc cosine of A. This we call alpha. So this is well defined. Okay, since so this means that since the cosine of alpha is A, just vice versa, it follows from this here that if the one is the cosine of alpha squared, then the other one must be the sine of alpha squared, just by this identity of sine and cosine. So this equation here yields B squared is the sine of alpha squared, and this means that the absolute value of B is the absolute value of the sine of alpha. Now we only have to check if we have the correct sign. That's the problem here. Now we define, so alpha is something we've already seen, and now we have the sine of alpha, and we define now phi to be a new angle, namely we take phi either to be alpha or minus alpha. So alpha if B is equal to sinus of A, and minus alpha if B is minus sinus of A, and we know from this equality that one of the two needs to hold. Okay, then it follows, in this case, because the cosine has symmetry properties. If we change the sign here, the cosine doesn't change. We know that A is also the cosine of phi, and by construction, B is the sine of phi. So this means, just by definition of our R and phi, Z is the same as R times the cosine of Y plus I times sinus of phi, whoops, like this. Yes, because, sorry, yeah, no, like that. Okay, sorry, this was the rescale, so this is the number W, and we just put the R again in front to get Z back, and this is just by, we know that this is by Euler's formula the same as R times e to the I phi. And so we found our representation of Z in polar coordinates. So the equality, if we just change sign, if we change the angle by a multiple of 2 pi, I just put in the lecture notes, just a simple computation. So let me end it like this. Okay. And now let me just give you from this proof method a slight overview, namely how can we get from one representation to the other. I just want to have this once on the board explicitly, and this is something you kind of need to know to compute with complex numbers properly. First of all, from polar coordinates to ordinary coordinates. So if this is easy, if Z is R times e to the I phi, and we want to display this as real part plus I times imaginary part, we can just use Euler's formula. This is r times the cosine of phi plus I times r times sine of phi. So here we get real and imaginary part directly. Sorry, I just made another mistake and used the opportunity to erase the board at the same time. So how to get from ordinary coordinates to polar coordinates? Here we can just basically re-obtain the method that we used to prove the previous theorem, which basically told us already how to get the polar coordinates. I just want to summarize it again. So if we have z as x plus I y, then first of all we've seen that this r, this factor, has to be the absolute value. And this is of course the same as by definition, the square root of x squared plus y squared. And so we have these two numbers and have to insert them there. Now for the angle, for phi, we have to use the arc cosine, and now it depends just on the case if y is positive or negative. We had this ambiguity in the proof there, and this turns out to be the arc cosine of x divided by r if y is non-negative, and minus the arc cosine, that was kind of when we changed the angle to minus the angle at some point, of x to the r if y is negative. Okay, this is how we can compute then in this case the polar coordinates directly. As a final bit in this section, I just want to show you basically one last corollary, because this shows that in terms of polar coordinates it's sometimes much easier to compute, and I don't want to prove this, I just want to present to you kind of how to do a complex computation at this point, namely for each n and n, the equation, in our very simple and important equation, z to the power of n is equal to 1. So this equation here has exactly n solutions in the complex numbers, if you consider this as a complex equation. Just like that. And you can do this then simply by computing, and you get these are, so we get explicit formulas for them. So this is just the set z0, z1 to zn minus 1, where these numbers are given as follows. Zk is simply e to the following, I times 2 pi k divided by n for all k. And this is something you can just prove directly from the things that we've already seen in this section. So I've just put this proof in the lecture notes. Okay, this finishes chapter 3. So now we've got ourselves a nice zoo of functions. We have exponential functions, we have logarithms, so general powers, sine, cosine, and so on. And now we have, this means that we have a lot of examples that we can study of functions. In the next chapter, we will kind of increase our methods by including differentiability and derivatives of functions. And there also we can compute basic derivatives of everything we've done so far and then use them to really have some nice applications. And see you in the next chapter.